Hello, my name is Zaid Fackenthal, and this is my surfing physics project. This project was inspired from the huge waves 2 weeks ago on Oahu, Hawaii. These are averaging around 70 feet high, and I just got inspired from one of the YouTube guys I watch, him catching the waves, and I'll show you a bit of him later. All right. So the questions we're going to be answering today that I personally had were given, say, a wave height and like the interval between the waves called the period. How fast are these waves? And then what is the difference between the work and the kinetic energy of me just paddling for a normal 6-foot wave, or the crazy guys being pulled from a jet ski and catching the 70-foot, 60-foot huge waves? So we'll be finding that out. And then also explaining why you can't paddle for those huge ones. It's nearly impossible. You have to be pulled from a jet ski. So we'll be showing that later. And lastly, say one of these expert pro guys catch the huge wave, 70-foot, right at the top. They're going a certain speed, certain height. They zoom on down to the bottom. How fast are they going to be at the very bottom? All right, now I'll show you a bit of that context. Let's go over and see what the news has to say about this.
The biggest swell seen in years is hitting most of the state's north-facing shores. Here's a live look at pipeline from Surfline cameras. As you can see just how powerful these sets are coming in.
So huge waves. Those don't look very big, but now I'm going to show you Jamie O'Brien. This is the guy I like watching. Biggest waves of my life, swell of the century. Being pulled by a jet ski, as you see. Here's the huge wave I wanted to show you guys. All right. So first things first, find the speed of the wave. Okay, I found this nice shallow water wave calculator. And you're given a height. I looked at the average thing there. It was pretty huge, 70 feet. And then the period, that's the distance between one wave and the next wave coming up to that same spot. So the period then was 20 seconds. And then hit calculate, and you get all this really cool information: the steepness, wavelength, amplitude, transition zone, the height of where the waves are underneath to hit the ground. But the thing we really need right here is the group velocity. It's right here. And that is 30.3 knots. So let's write that down. So we got speed of a wave given 70 feet and 20 seconds. That gets us, we have 30.3 knots, but that's not really what we want. Come here, put in 30.3. That's the same as 35 miles per hour. Still not quite what we want, but that gives you guys a little bit of context. Let's get meters per second. 15.6 meters per second. And that's how fast the waves are going when they're 70 foot high and there's 20 seconds in between them. All right, so next thing we're going to want to find is the amount of work / kinetic energy to catch a wave. This is the difference between, oh, I'm just paddling, catching maybe a 6-foot wave, nothing crazy. And the pro guy's being pulled from a jet ski at 35 miles per hour to catch the 70-foot waves. So let's first find, let's find out what the jet skis are doing. So equation we're going to be used is kinetic energy is equal to half mass times velocity squared. So for mass, I am roughly 145 pounds, which is equal to 65 kilograms. So now copy this here. We're going to find, so mass is going to be 65 and velocity is going to be 15.6. I got the my mass from here, kilograms, we want to use that. And I have speed, velocity, I get there. Okay. And that gets us roughly to 7,909 joules. Okay. Now we're going to contrast to the difference amount of kinetic energy it would take me. I calculated how fast I go if I was paddling, just normally in my wetsuit up here in Washington. And I accelerated roughly, actually, let's put this up here. I accelerated roughly 1.5 meters per second squared. So that's acceleration. Obviously, that's not what we want. We want velocity. So squared. So if I multiply that by seconds, then I'm going to get my velocity. What seconds do I use? It depends on how fast it takes me to catch the wave. I don't want to really say how fast it takes me to catch the wave, so I'll say 3 seconds. That seems reasonable, right? So multiply that out, you get 14.5 meters per second. And that's roughly 10 miles per hour. So come down here, let's copy this equation. 1/2, same weight there, but now instead of 15.6, I'm going to use the 4.5. And this is where I get an answer of 658 joules. So you can see difference between these is quite large, and just from me trying to go 4.5 to catch a wave as opposed to 15.6 meters per second. All right, so this is the amount of work. Now, let me check. Yep, so these are nowhere near each other. Not gonna be catching any of those huge waves. It's gonna take way too much. Jet ski can do a lot better. But let's prove even further. Let's see how much how much force and how hard it would be for me to just paddle normally to catch one of those huge waves. So we are now going to do force times distance graphs, a jet ski versus me paddling. So we're going to be creating some graphs. Not quite sure what our units are going to be. We know one side's going to be force distance, and the area underneath the line is going to be our work. Well, it's going to be kind of opposite because we don't know the distance it would take. We know the work. We got this up here, that number there and that there, but we don't know distance, and we can actually calculate force. So force is equal to, let me go here. Force is equal to mass times acceleration. All right, so if we find, we use the velocity that we had before, 15.6, we're going to figure out what our acceleration would be. So we have acceleration is equal to meters per second per second. I am given 15.6 from up here, 15.6 meters per second, but then we have to divide it by another second. How many seconds we're going to use? We're going to use 3 seconds, like I used in the previous example, keep things fair. 3 seconds. And we get roughly 5.2 meters per second squared. All right, that's as opposed to my previous acceleration of 1.5 meters per second squared. So I always do that. Meters per second squared. So 5.2 versus 1.5. Okay, so we got the acceleration. Now we got to calculate force. So force is equal to mass times acceleration. My mass, which we had up there, was 65. As we used in all the other examples, that's my weight. And then I for my acceleration. Let's first catch the huge waves. Let's do 5.2. That's going to give me a force of, let's see here, 338 newtons, as opposed to 65 times 1.5. Move this back a little bit, which is equal to 98 newtons. All right, so we got our force here. Now let's make us some graphs. So we're going to need the work. So let's copy this work here. So we got under jet ski. The jet ski, we have our work of that. We got our our force of this, 338 newtons, as opposed to paddle of 658 and a force of 98 newtons and joules. All right, so now we got to calculate the distance. Okay, we got our equation. We got the equation. Let's put it up here. Force times distance equals work. All right, so if we divide work, let me get this. We divide work by distance. If we divide work by force, divide by force, then we'll get distance. So let's clear that. So our distance is equal to 7,909 joules divided by 338 force. We get a distance of 23 meters. All right, so 23 meters, that's how long it would take me from going on a jet ski to catch these huge waves. Now for me paddling, distance equals 658 divided by 98, and we get 7 meters. All right, so seems reasonable. Let's put a graph on these. So I have to figure this out. Bear with me. Draw graph. Let's do that. Okay, so let's make a graph. Make it a little bigger. So we got our graph. This is going to be force. This is going to be distance, and we got our work. So what are our two numbers we're going to be using? For force, we have this and this. So let's do 100, 200, 300, 400. So we got one that's going to start roughly right here, or right here, and one's going to start roughly right there. Okay, for distance, we got 23 and 7. So let's do 5, 10, 15, 20. So we got 400, 100, 10, 20. I'm not going to spend your time filling that all in. All right, so so force 338. It's going to be roughly right here, going along in a line, and we're going to stop at where we think 23 is. And the area under this is going to be 7909, and that is our work, 7909 joules. If I was just paddling, 98, go out to 7, and we got our work of 658 joules. All right, so see, this scales pretty nicely. Now, further point to prove why I can't be going along and trying to paddle for these huge waves. Let's say I take, we're calculating distance, say I take the amount of work, 7.9, it takes to catch one of those huge waves, but I only divide it by 98. 98 force. This is how me just paddling for it normally. And we get the distance it would take for me if I was just trying to paddle, non-stopping, trying to accelerate to meet this wave. Let's see how long it would take, how far it would take for me to go. And we get 81 meters. Just to show this on the graph, we're going on here. Oh, we're going on here, 98. Oh, you can't see that very well. Going on here. We're going. That's only 20, 4 times that far. I can't really, yeah, I can't show it. You're going on all that far just to get that amount of work. It's not happening as much as I would want to. All right, so now I got to clear all this. And now that is the work and kinetic energy to paddle versus jet ski. And now kinetic energy at the bottom of a wave. All right, so I caught the wave totally, right? I'm jet skiing it on. We have the equation we're going to use, potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. So potential energy is mass, gravity, height. Kinetic energy, like we did before, 1/2 meters, I mean mass velocity squared equals mass gravity height plus 1/2 mass velocity squared. Okay, so now we just plug in our numbers, and actually everything here has a mass, so we could actually divide by our mass and not have to worry about it. It's nice. Okay, so come down here, gravity 9.8 plus 1/2. My initial velocity has to be what I said, like being pulled by a jet ski, has to meet the wave, the velocity of the wave. So 15.6 squared equal to, oh, whoops, I mistyped. 9.70, or not 70, 70 feet. That converts to 21 meters. All right, plus 1/2, 15.6 squared. That is equal to 1/2 our unknown velocity squared. So that number there goes to 2 equals 206 plus 122 is equal to same thing. Just going to copy that there so you don't have to worry about it. Now, if we get divide, if we add this together, multiply by 2, we get velocity squared is equal to 656. Divide that out, our final velocity is going to be equal to 28 meters per second. We go meters per second to miles per hour, which is 58 miles per hour. That's how fast you're going to be going at the bottom of the wave, catching it from the 70-foot tall. Yep. So that is my physics project. I've shown you how the speed of the wave, the amount of work it takes and the kinetic energy to catch the wave, kind of contrasted that. And come down here, the force and distance graphs. We calculated the work and force of a jet ski versus me just paddling for a 6-foot wave. And then how far it would take as opposed if I try to paddle, just saying I'm working that whole time, that's how long it would take for me to paddle. And kinetic energy at the bottom of the wave. And that's it. All right, hope you enjoyed this kind of tutorial-like demonstration. Thank you.